even if you have the perfect chunks created from your documents, you're now faced with the problem of finding the correct one given a user query. How do you do that? One way would be to use a simple keyword search, but you quickly realize that the chunks that are being returned are not those semantically similar to what the user is asking. So in order to improve on that, we're going to be using semantic embeddings, and I'm going to show you how you can use a local vector database that is going to store the embeddings and allow you to search within it. Let's get started. Embeddings are vectors or simply a list of numbers that can represent your text into a highly dimensional space, and within this space you are allowed to search for closeness. So for example, if you have the word of king and queen, you can use a similarity metric that is going to tell you, okay, so how far the queen vector is from the king vector, and when two or more vectors are close together, you might deduce from that these vectors are indeed semantically similar. This is the idea behind using embeddings for retrieval and RAG applications, and I'm going to show you how you can implement this in a very simple toy example. If you want to get access to the complete source code along with a complete text tutorial, go and subscribe to MLExpert Pro. There, you're going to find a complete AI engineering academy that starts from the basics of statistics, machine learning. Then you're going to go through how you can deploy your own machine learning models to production. Then you're going to go into LLMs, RAGs, CAGs, and AI agents. So if you want to become a better AI engineer today, go and subscribe to MLExpert Pro. Thank you. I'm in my local cursor instance, and here you can see that we have a vocabulary of words. Those words are roughly speaking into two different categories, royalty and food. So here, for example, we have king, queen, royalty, then for the food one, apple, pizza, eat, food, etc. And here are embeddings, and note that those embeddings are actually going to be learned on their own in production systems, but here just for this toy example I have the embeddings hand coded, if you will. So you see here that the dimension 1 is high. For the royalty embeddings, that means that it is closer to 1, while for the food embeddings here we have this number or this part of the vector very close to 0, and here on the right side, or the last dimension if you will, we have the royalty embeddings to be very close to 0, essentially flipped here for the food embeddings. So given that, we are going to be building this dictionary, which is going to give us a word to embedding dictionary, and for each word from here we're going to be able to get the vector that represents the embeddings of this word. To get the embedding for a complete sentence, we're going to be using the get sentence embedding function. And what this function does is that given a sentence, it is going to split it into multiple words, and each of those words is going to be getting an embedding from our previous dictionary, and all of the embeddings for the words are going to be average, and this is going to be the result of this function. If a word is not within the dictionary, this word is going to be simply ignored. Now we have our first example. We have a document that we're going to be using as a baseline. The king has power on the throne, and then we're going to be having this related query. The queen has a royalty, and one unrelated query, eat pizza and apple in the kitchen. So we're going to be getting the embeddings for each of those, and we're going to be also getting an embedding matrix right here. So after we do that, I'm going to show you the results of the document, then the related query and the unrelated query. So even from here, you're going to be able to see that the dimension of the document, that is the first dimension here, is very close to the related query. The second one seems to be more related to the unrelated query, but on the third one, we have very similar numbers here for the document and the related query. And based on that, we're going to be calculating a cosine similarity. So this is going to give us the distance between two different vectors. It is a very common metric for that. And as you can see here, the formula for calculating this is very simple. We're getting the dot product of the two vectors, then the norm of the first and the second one, and then we're going to be multiplying that, and this is going to be within the denominator, and in the numerator we're going to be having the product of the vectors themselves. So after that, we're going to be calculating the similarity scores for both the related and unrelated query. And you can see here that the related query has much higher score from the cosine similarity, while the unrelated query is very far away from the document itself. These numbers should be between 0 and 1. And of course, 1 means very related or very similar, while a number close to 0 is very dissimilar or unrelated. We are going to continue with a pre-trained embedding model, and I'm going to show you how you can use that into a LangChain application. So here we have the chunks from the previous video, or at least some of those, and two additional chunks that are coming from NVIDIA's financial results. So we have a mix of customer complaint policy PDF and two chunks from the NVIDIA financial results, and I'm going to be loading each of those into a list, and then I'm going to be using a fast embeddings. This is going to allow us to use local models, and in this case this is going to be the BGE small English only embedding version 1.5, and I'm going to be calling the embed documents on that, and this is going to look into what is the dimension of the vectors that the embedding is going to provide for us. This is going to be important since we're going to be storing this into our vector database. And a single embedding looks something like this. As I have already told you, these are just vectors with floating point numbers. So you can see the actual values right here. And let's try the embedding model. Here is a query that I'm going to be using. What are the responsibilities of the management team? And you are going to be able to embed your query. So now we have a vector embedding for our query and a vector embedding for each of the chunks that we have. And if we calculate the similarity score with cosine similarity function that we already have, you're going to be able to get a list of similarity scores. And as you can see from even this list right here, you can see that the first chunk is actually the closest. Let me show you how this looks like into a data frame. And again, you are going to see that the chunk with the index of 0 here, we have for this chunk the highest score. So this is the sorting or the order of the chunks by how similar this chunk is to the query that the user is giving us. And just to make sure that this is indeed the chunk that must be the most similar to what the user is asking, you can see that the context that we have created is that this chunk outlines the responsibilities of the management and employees in handling customer complaints. Another way to look into what the embeddings are showing you is to visualize the query along with the different documents that you have. In this very simple example, we have only 4, but in the real world, you can even do this with multiple documents or multiple chunks. Here you can see the distance from the query, which is essentially within the center of the screen, and the chunk number 1 is going to be the chunk that is going to have the highest similarity score. And in this case, this is going to be the closest chunk actually to the query. So we have essentially flipped the distance. The smaller the distance, the higher the similarity. Here you can see the cosine similarity for chunk 2, chunk 3. In the notebook that I have shown you, we are using a very small embedding model, and this model might work perfectly fine for a small application that needs to run fast. But if you have requirements to run this type of applications with as best possible embeddings that you can get. You can probably use the MTEB leaderboard, which is an embedding leaderboard. And as you can see here, even on this leaderboard, you can see that our model that we're using is relatively small. There are even better choices. And in particular, if you go here and look at the tasks, you can now get a leaderboard that is specific for retrieval tasks, since this is the task that we're going to be needing in order to create our RAG application. And one very important thing here is that open models in the face of Quentry embedding are on top of the leaderboard. So you can use Quentry embedding, for example. The 4 billion parameter model looks like a good spot. Even the 600 million parameter model is quite strong, and you can use this with a GGUF version and deploy it and look into how your RAG performance might increase on that. Of course, all of this is subject to further evaluation for your particular use case. You have the vectors for your embeddings, and now you need to store them somewhere. One place for that would be to use a vector database that is a dedicated system that allows you to store your vectors, and there are a lot of them. There is an article called Why Vector Databases Are a Scam, and in this case, this might be true or it might not be. Of course, it depends on your use case. In my experience, for most systems, you don't need a dedicated vector database. You need something as an extension to existing database. So for example, I really like pgvector, or even for SQLite, there are vector embedding extensions that allow you to store your vectors into your classical SQL databases. One very important benefit of that is that your company most probably already have a database, and you're going to be adding an extension or an upgrade that allows you to even store vectors within it. With that, you don't need another system that you're going to be able to deploy, add additional resources for that, and create and learn a whole new APIs and software that you need in order to keep this instance running. If you're able to stick with something like pgvector and use that in production, this is currently my recommendation to you. Of course, vector databases do have their place, but that place is where you have something very highly specific and highly valued as well. We are going to be using Postgres as our vector database along with the pgvector extension. All of this is going to be wrapped into a Supabase instance. Again, everything is going to be running locally on our machine, and Supabase makes this extremely easy with a very nice UI interface for you to interact with. In my terminal, I have created a new directory that I'm going to be calling just Supabase. Here I'm going to be using Supabase init. I don't want this to use Dino setup for VS Code and IntelliJ. After that, I'm going to be calling Supabase start. Here you need to have a local Docker instance, and this is going to start the process of running everything. After the build and run is complete, you're going to be able to get the studio URL, which is this one right here. This is going to open a local UI instance. You are also going to be presented on a bit further down, if you scroll here, to the keys that we are going to need in order to connect to our local Postgres and Supabase instance. After you open the Supabase UI, you're going to be presented with the screen that you're seeing here within your browser. And if you go to the SQL editor right here, I'm going to be pasting the SQL query that is going to be added by LangChain in order to communicate with your Supabase instance. The only difference here is that I have modified the number of embeddings that we're going to be using, since our embedding vector is going to be 384 in dimension, which is the fast embed model that we're using. Also, this will enable the extension vector or PG vector. We're going to be creating a table called documents, which will contain the ID of the document, the content, which is going to be the text, the metadata. This is going to be a JSON field, and then we're going to be storing the embedding vector itself. This also adds a new function called match documents, and this function is going to do the heavy lifting for us, or the similarity search. And I'm going to be pressing run here, and this should now create the documents table here within the table editor. As you can see here, we have the ID, the content, the metadata, and the embedding vector. Back in my Wacom cursor instance, here is the environment example that we have. You need to create a .env file within your root folder of the project, and you're going to be passing the Supabase URL. Of course, if your Supabase instance isn't running on your Wacom machine, you need to replace this here, and you're going to be able to provide the Supabase service key that was given to you when you run the Supabase start command. After that, you should be able to create a new Supabase client, which we're going to be creating with the create client function. Let me run this. And after that, we are going to be creating this Supabase vector store, which is coming from LangChain. And this is going to get the embeddings function or provider that we have along with the Supabase client. Here we have the table name, which should match the one that we have added into the SQL, and then a query name match documents, which is the function that we have created. After you run this, you are going to be able to add additional documents to your vector store. In our case, these are going to be the chunks that we're going to be adding. Note that I'm also adding metadata to each of those, and I'm going to show you why this might be a good thing to do. I'm going to be adding each of those documents and then calling the add documents, and this is now going to go and add the documents to your Supabase vector database. When you go back to the studio of your Supabase instance, you are going to be presented with the newly added documents right here. Again, this is within the table editor and then documents. So here you're going to be able to see the complete texts along with the embedding vectors, which is pretty interesting. Of course, you might go into the numbers on your own. And here you can see that we have even added the metadata, which is a binary JSON or JSONB, which contains the metadata of the part and then the source of the document that we have provided. Now that we have the documents within our Supabase instance and we have checked that they are indeed there, I'm going to be using the similarity search with a relevance score for the query that we had before. This is exactly the same query with a k equal to 2. So I want at most 2 documents to be returned from our vector store. And now we should pretty much get exactly the same response. Yes, this is the chunk that outlines the responsibilities of management. If you don't remember the query itself, let me show it again. What are the responsibilities of the management team? And here we have the score of 0.66 almost, with the content chunk and the parts of the metadata right here. Then the second chunk is the one again from the customer complaint policy document, and this again has much lower score, but still it is in second place. So our k equal to 2 filter is actually working pretty good by giving us just the 2 most relevant documents for this query. You now have your vector embedding stored in a database, and even a crash to your system shouldn't be able to wreak havoc on your production environments. And another important feature of storing and using a vector database is that you can apply additional filters to how you want your results to be returned. So in this case, I'm going to be reusing the same query but this time I just want to get access to the documents that are within the NVIDIA financial results. So let me run this. And here you can see that we're using exactly the same method, similarity search with relevance scores. And this time I have the filter of source equal to NVIDIA financial results. This stew is going to give us two different results since we have two chunks right here. And for example, if I run this with k equal to 3, yeah, you can see that this is even now bounded by the number of the documents. So in this case, we're going to be having the first chunk and then the second chunk. Note that even if we're filtering just the NVIDIA chunks, the scores and the results are still relatively low. So if you want to have some sort of a threshold that is going to be cutting off the documents that are not above it, this might be a good example. In this video, we've seen how you can turn your text chunks into vectors and store those vectors into a local database. In our case, this is Postgres via Supabase. We've seen how you can turn your text into meaningful chunks that we can use to search by meaning, not just keywords. In the next video, I'm going to show you a bit more advanced techniques on how you can improve your RAG, and we're going to be able to pass our context to the LLM and finally see some results based on the user queries that are going to be answers by our AI models. Thank you for watching, guys. Please like, share, and subscribe. Also, join the Discord channel that I'm going to link down into the description of this video. If you want to get access to the complete source code and text tutorial, go and subscribe to MX Tutorial. Thank you, and I'll see you in the next one. Bye.